Almost all autonomous vehicles are equipped with LiDAR, and point clouds with semantic segmentation can be applied in many areas, such as obstacle avoiding or object manipulation. Our project proposed a pure range image unit to the semantic segmentation of the point clouds. It is a neural network based on encoder-decoder architecture that takes in 2D range image. Thus, it has less computational time than the traditional methods and could be used for real-time scenarios. We used the SemanticKITTI dataset for our project. It provides 22 LiDAR sequences from different outdoor driving and a pool of 28 classes to map the whole environment. Half of the sequences are labeled so we can use them for training the network. Here is an example of the point cloud data, and we used it to generate the range image. Due to computational limit, we tuned the angular resolution to 0.31 degree. The maximum angle width were set to be 360 and 180 degree respectively, and these were generated from the full scan and half of the scan. After getting the range image, the label associated with each pixel was computed using the KD tree. The corresponding labels were then extracted from the .label file by index, and we can use them for the network. The PRI-Unet architecture is an encoder-decoder. The encoder is in a repeated application of two 3x3 convolutions, followed by a max-pooling layer that downsamples the input. The second half upsamples the input, and concatenation is done to capture global details. After that, two 3x3 convolutions are applied, and this block is repeated until the size matches the input. Finally, the last layer is a 1x1 convolution that outputs as many features as we wanted. The model was trained and validated with sequence 0 to 10. We used the smaller half datasets for training and the others for testing. We compare their classification accuracy for the performance. We have the quantitative results on 11 sequences for 19 semantic classes. The PRI-Unet did better in some classes, and on average, it performed similarly comparing with other models. However, it doesn't have many layers, and it's easier to implement. Here's an example of the prediction result. The predicted point cloud on the right side is very similar to the ground truth on the left. We also plotted the trajectory and the labeled map by BKI Semantic for individual sequence. Zooming in, we could get more details about the labels. In conclusion, we have successfully implemented the PRI-Unet. The result is comparable to other models, but we have a simpler network and smaller input data. One thing we learned from this project is the importance of computational power. We used Google Colab for this project, but if we have powerful hardware, we could further improve the results. Please refer our paper and Github for more information.